Hello and welcome to this video on modelling with differentiation. Imagine that we have a sheet of A4 paper which we want to fold into a cuboid. What height should we choose for the cuboid in order to maximise the volume? Or we have 50 metres of fencing and want to make a pen of the following shape such that the area is maximised. What should we choose X and Y to be? These are examples of optimisation problems. We're trying to maximise or minimise some quantity by choosing an appropriate value of a variable that we can control. Optimization problems in an exam usually follow the following pattern. There are two variables involved. You may have to introduce one yourself, typically lengths. There are expressions for two different physical quantities. One of these is a constraint. For example, the surface area has to be 20 centimeters squared. The other we wish to maximize or minimize. For example, we wish to maximize the volume. We use the constraint to eliminate one of the variables in the latter equation, so it's then just in terms of one variable, and we can then use differentiation to find the turning point. We are going to look at several worked examples, starting with this one from the textbook. A large tank in the shape of a cuboid is to be made from 54 meters squared of sheet metal. The tank has a horizontal base, but no top. The height of the tank is x meters. Two of the opposite vertical faces are squares. Part A, show that the volume, V meters cubed of the tank, is given by V equals 18x minus 2/3 of x cubed. So firstly, we have this constraint. The surface area has to be 54 meters squared. So let's form an expression for the surface area. There are two square ends, each x by x, so that makes 2x squared. And then because there isn't a top, there are three rectangles, each of x by h, so 3xh. And the total surface area, 2x squared plus 3xh equals 54. We then make h the subject because we're looking to get a formula for the volume only in terms of x. So we want to eliminate h from the volume formula when we get there. So if we take away 2x squared and divide by 3x, then we get that h is 54 minus 2x squared over 3x. And writing that as two separate terms, that's the same as 18x to the negative 1 minus 2/3 of x. Now the volume, even though there's no top, the volume is the same. It's x squared h. And if we replace h with what we've just worked out, we get x squared multiplied by 18x to the negative 1 minus 2/3 x. And if we expand the brackets, we get the answer we wanted of 18x minus 2/3 of x cubed. Part B says, given that x can vary, use differentiation to find the maximum or minimum value of v. So we've got v in terms of x. dv by dx is 18 minus 2x squared. And since we're looking for a turning point, a maximum or minimum value, we want to put that equal to 0. Solving the equation, we get that x squared equals 9, and hence x is plus or minus 3. But as we know, x is a length, so the negative value won't be allowed, and therefore x has to equal 3. So the volume itself, going 3 back into our formula, we have 18 times 3 minus 2/3 of 3 cubed, which is equal to 36 meters cubed. And then part C, justify that the value of v you have found is a maximum. So if we use the second derivative, we get negative 4x. Now, since x is a positive value, we know that negative 4x is going to be negative. But the exam often like you to actually substitute the value in and get an answer. So since x is 3, negative 4 times 3 is negative 12. And since that is less than 0, it's negative, that implies that we have a maximum as requested. Okay, a second worked example. I have 216 square centimeters of cardboard and I wish to make a cuboid box which is 4 times as long as it is wide. Find the maximum volume it could be. So again, I have a constraint. It's the 216 square centimeters of cardboard. That's the surface area. And we're trying to maximize the volume. So what we're going to do, we're going to get the surface area and the volume. They'll both be in terms of two variables. There'll be the as you can see from the diagram, I've labelled x and 4x to represent one length, which is 4 times as long as the other. And then in the other dimension, we've got the height as h. So we have our two variables, x and h. So for the surface area, there are 6 faces in total. It's not an open box like the previous one. We've got an xh on the left-hand side. We've got an xh on the other end. On the bottom, we've got a 4x squared and the same on the top. And then the other two rectangles are both 4x times h. And if you add that all up, you get 8x squared plus 10xh, equaling our constraint of 216. And then rearranging that to make h the subject again, we get 216 minus 8x squared over 10x, which again has two individual terms, is 108 fifths of x to the negative 1 minus 4 fifths of x. And then for our volume, that's 4x squared h, and if we substitute for h, we end up with a final answer of 432 fifths of x minus 16 fifths of x cubed, which we will then differentiate on the next slide. So for dv by dx, we have 432 fifths minus 48 fifths of x squared. We put that equal to 0 because we're looking for the maximum. And then after solving that, we get x equals 3 again, just like in the previous worked example. And again, to work out the volume, we substitute x equals 3 into our volume formula, and we get 864 fifths centimeters cubed. Now in this question, we haven't been asked to justify that it's a maximum, but we can do. If we find the second derivative, we get minus 96 fifths of x. And as I said before, since x is a positive number, that is definitely going to be negative when we substitute our positive value into it. Hence, we have a negative value and it's a maximum. Okay, so we've been looking at maximizing the volume for a constraint of a surface area. Let's do it the other way around. So find the minimum possible surface area of a cuboid box which has a volume of 121,500 centimeters cubed and which is 3 times as long as it is wide. So best thing to do, I think, is to draw a diagram, as you've seen in the previous two questions. This time it's 3 times as long as it is wide, so the base I've written as x and 3x with our h in the third dimension. So this time our constraint is the volume. So starting with that, the volume is 3x squared h, and that equals 121,500. And then making h the subject, that means dividing by 3x squared, and we can rewrite that as 40,500 x to the negative 2. For our surface area, the total surface area is 6x squared plus 8xh. Substituting for h, we end up with 6x squared plus 324,000 x to the negative 1. And again, we can then differentiate that to find our minimum surface area. So dA by dx is 12x minus 324,000 x to the negative 2. We put that equal to 0. One way of solving this equation is to times everything by x squared, which gives us 12x cubed minus 324,000 equals 0. And then adding 324,000 to both sides and dividing by 12, and then cube rooting, we get x as 30. And this time, if we want to work out the minimum possible surface area, we want to substitute our x equals 30 into our area formula, and we get 16,200. And the units, look back at the question, the volume was in centimeters cubed, so our area is in centimeters squared. And again, although we haven't been asked to do this, we can check that it's a minimum rather than a maximum. The second derivative is 12 plus 648,000 x to the negative 3, which you could rewrite as 12 plus 648,000 over x cubed. And again, we know that x is a positive value because it's the length. Therefore, that expression is going to be positive. And if we have a positive second derivative, that means we have a minimum. Okay, so far we've looked at 3 cuboids. Let's finish off with a cylinder. So solid cylinder C1 has a surface area of 294 pi centimeters squared. Find its maximum possible volume. So, as you should remember, the surface area of a cylinder is given by 2 pi r squared plus 2 pi rh, and that is equal in this question to 294 pi. We can divide through by 2 pi to give us r squared plus rh is 147, and then making h the subject gives us 147 minus r squared all over r, which can simplify to 147 r to the negative 1 minus r. The volume of a cylinder is given by pi r squared h, so substituting our expression for h, we get 147 pi r minus pi r cubed, from which dv by dr is 147 pi minus 3 pi r squared. We put that equal to 0, because again we're looking for the maximum. Divide through by 3 pi, we get r squared is 49, and r is 7. Of course it can't be negative 7 because it's a radius. And then substituting 7 back into our volume formula, we get an answer of 686 pi centimeters cubed. And then finally, just for completeness, if we do the second derivative, we get negative 6 pi r. And again, since r has to be positive because it's a radius, negative 6 pi r is going to be less than 0. And hence we have a maximum. Thank you very much.